Okay, so today I am going to discuss another problem from magnetostatics, and this problem is from Griffiths. And this is actually an important problem because most of us know the infinite solenoid problem, where you have an infinite solenoid with n turns per unit length, current I is flowing, the magnetic field at the center along z axis is mu naught n I. Okay, so this formula is known to you, but suppose you have a finite solenoid of length, suppose L, not infinite, then what will be the magnetic field at different points? Suppose this point, suppose this point, suppose this point. So the magnetic field at different points will be different, okay, and how you can calculate the magnetic field at a particular point. So this is the point P, and you have to calculate the magnetic field. They don't give the total length L, but you can assume it the total length PL, and they actually give the angles theta 1 and theta 2 actually. Okay, so basically if the total length is L, then cos theta 1 and this distance is suppose D, then cos theta 1 is your D by root under D square plus A square, and cos theta 2 is basically your D plus L divided by root under D plus L whole square plus A square. Okay, so basically these are the things. If D is the distance and L is the length of the solenoid, they are given in terms of angle because this looks more pretty because the final answer will look more pretty actually. Okay, so this is the problem. You can read this problem by yourself and pause the video, give it a try by yourself first, then you look at the solution. Okay, so TIFR also asked this kind of problem in previous year. They give this kind of a finite solenoid and ask the magnetic field in a particular point. This kind of problem they asked in previous year. Okay, so let's now jump into the problem. Okay, so this is your solenoid, finite solenoid. Okay, and in turns per unit length, A is the radius, in turns per unit length, A is the radius, I is the current, and here is point P, and now you have to calculate the magnetic field. So the fundamental thing you have to know to solve this problem. See, this cylinder is what? Cylinder is the constitution of infinitely many rings. So there is a ring, there is a ring. If you pack up this all the rings, then it will form a finite solenoid, a cylindrical shape. Okay, so there are many rings. Okay, so basically you have to take some distance. Say, let's say this is the distance x you are taking from this, and a small length element dx, let's say this is the length element dx, and this is like a ring. Okay, there are many rings inside this small length element dx. And what is the magnetic field due to ring? This is the fundamental thing you should have known. Okay, otherwise you can't solve this problem. So magnetic field due to a ring at a distance x is mu naught I by 2 into a square divided by a square plus x square to the power 3 by 2. Okay, this is the fundamental formula for you need to solve this problem. Okay, and you can also verify this. Just put x is equal to 0, you will get your usual magnetic field at the center. Okay, so put x is equal to 0 just. Okay, so this is the fundamental formula you should have know to solve this problem. Okay, now this is the distance dx, this is the thickness dx, and n is the number of turns per unit length. Okay, so unit length consists n number of turns. So dx length consists n into dx number of turns. So there is one turn, two turn, three turn, four turn. If you combine this all these rings, it will constitute n dx number of turns. Okay, now dx is very small, so you should have think according to the calculus that b will not change with these distances. Okay, so a single ring produces this b, so a thickness dx constitute of n dx rings. So the magnetic field due to the n dx rings is equal to mu naught I by 2 n into dx. Okay, so this is the number of rings present in the thickness dx into a square divided by a square plus x square to the power 3 by 2. Okay, so this is due to the n dx rings. Now what is the total? We have to integrate it simply. Okay, so mu naught in I is square by 2 integral of dx into a square plus x square to the power 3 by 2. Okay. Now let's see, they have given in terms of theta. Okay, so let's try to convert the integral in terms of theta. This will be more helpful. Okay, so let's suppose this is theta. Okay, and this distance is x, this distance is a. Okay, so what is tan theta, or let's say tan theta? Yeah, tan theta is equal to a by x. Okay, so x is equal to a cot theta. Yeah, so your dx is equal to minus a cosec square theta minus a cosec square theta d theta. This is your dx. Okay, so let's now substitute it. Mu naught ni a square by 2 dx is equal to minus a cosec square theta d theta into a square plus a square cot square theta to the power 3 by 2. Okay, so mu naught in I is square by 2 into a, if you a square to by a square to the power 3 by 2, a square to the power 3 by 2 integration of cosec square theta d theta to 1 plus cot square theta is cosec square theta, and cosec square theta to the power 3 by 2 is equal to cosec cube theta, right? Cosec cube theta. So mu naught in I by 2, yeah, integration of minus cosec square theta by cosec cube theta, it is simply sine theta d theta. Okay, is equal to mu naught in I by 2, simply you get cos theta. Okay, so if your limit is theta 1 to say theta 2, that means suppose this is your solenoid and it start at theta 1, it starts at theta 1 and it ends at theta 2. That means, let me draw it very clearly. So I assumed that this angle is theta. Okay, so suppose it starts at theta 1, that means it starts at theta 1 and it ends at theta 2, then your final answer will be mu naught ni by 2 cos theta 2 minus cos theta 1. So this is your answer in terms of theta, but you can again express in terms of d and l. So mu naught ni by 2 cos theta 2, that is d plus l divided by d plus l whole square plus a square minus d divided by root under d square plus a square. So let me clear what is d and what is l. So this is your length L and this is the distance D. Now suppose you want to measure this magnetic field at this point, at the center of this upper surface. So your D simply goes to 0. So mu naught in I by 2. D simply goes to 0, that means distance goes to 0. L divided by L square plus A square. So this is the magnetic field at this point. Now you can have this relation L is equal to suppose 2A or L is equal to A by 2. Then accordingly you will get different answers. Okay. Now suppose you want to find the magnetic field at the center. So your D is minus L by 2, right? If you want to find the magnetic field is at the center, then you start from this point and go in negative direction, and the distance you travel is L by 2, but it is in negative direction. Okay, so D is minus L by 2, right? So your B is equal to mu naught Ni by 2. D is minus L by 2, so L minus L by 2 is L by 2, and your L minus L by 2 whole square plus a square root under plus D is equal to minus minus plus L by 2 whole square plus a square. Okay, so this will be your answer. So you can find magnetic field at different points according to, you can use this previous result, that is theta 2 and theta 1, and you can use accordingly this result, and you can vary t, from positive to negative directions according to your conventions. Okay, so yeah, this is a good problem actually, and this is the fundamental thing you should have known. Yeah, so the formula of magnetic field due to a single ring, you should have know this formula for exam purpose. Okay, so yeah, this is a good problem, and that's it for today.